Okay, so let's have a class, and we will talk about the carbohydrates. Focus on monosaccharides today, and on Thursday we'll talk about vinegar. I do adjustment a little bit because fermentation comes from sugar, so we better talk about the sugar first. So this will be the carbohydrates. Carbohydrate, and we'll say number one. So first of all, we already know carbohydrates. What does this mean? Carbo is C, hydrate is H2O. And obviously it could be different C and different H2O. So that's a generic formula. And N could equal N, or M is not equal N. And the second, carbohydrates, we also call it is saccharides. And this is coming from a Greek word which is spelled as S-A-K-K-H-A-R-O. That means sugar. Okay, I cannot pronounce Greek word, but I know this is coming from that. That means sugar. So since it is saccharides, therefore we already know the carbohydrates basically have three different categories. We would say the first one easy is monosaccharides. Now monosaccharides, we will say it is a sugar we cannot further isolate it. So let's say glucose is a good example. Now we have a monosaccharides, and the second category is oligosaccharides. Oligosaccharides could be the monosaccharides unit somehow between 2 to 8. But most of the time we are interested about is a disaccharides. What are the examples? We already know, like lactose, like sucrose, and the sucrose basically is making the table sugar, and we already talked about that it's not a reducing sugar. Now with single units, long and long, we will have a polysaccharides. So what are the polysaccharides we have? Everybody knows we have a starch, and it could be a gum, it could be an agar. And we know we could eat starch, we could eat chewy gum, we could make agar plates for bacteria to eat it. So these, we all say it's digestible polysaccharides. However, there is some of the sugar, although we call it sugar, but we cannot eat it. Let's say chitin. Chitin is making like a chitosan, which is a structure of an insect. And we also have a cellulose. Cellulose, we know, we can make like a clothes, which is coming from a cotton. So this is something we cannot eat it. We also call them undigestible. And we will be covering the later lecture, talk about the manufacturing of the table sugar, and we're also going to talk about the starch, a little bit more detail later, next week. Now, we also want to mention about is that we talk about monosaccharides. Today, we're going to talk about monosaccharides. In our nature, most of the monosaccharides are deconfiguration, okay? So let's say glucose. Most of the time, we will say D-glucose. Now, how about L? Do we have an L configuration? Yes, we have. L-glucose, only very minimal in the nature. Sometimes it happens in polysaccharides as a components. And we will get to detail what means a D-glucose. Okay? So here, what we write is kind of like opening remarks. Give you a brief introduction. What's the carbohydrates we are talk about? Then the next thing, we want to give you an example. Then we go from there, talk about the detail. What is carbohydrates? Now let's give you an example. What is the simplest sugar? The simplest sugar is CHO. Right in the middle is HOH, CH2OH. This is the one you should know. You may not recognize it, but you should know. When we talk about the biochemistry cycle, talk about glycolysis, we have a glyceraldehyde 3-phosphate. We don't have a phosphate there, so this is the simplest sugar. We call this D-glycerols. D-glycerols. Now, why we call it D? Because this is carbon number 1, carbon number 2, and carbon number 3, and we have carbon number 2, the hydroxy group, which on the right side. So the D or L is determined by the hydroxy group attached to the carbon number 2. Okay, so this is determined by carbon number 2. So this is D-glycerols. And then, during we talk about the biochemistry cycle, we talk about there is a transition step. The transition step have another very interesting simple sugar is CH2OH, CO, and CH2OH. Now that name, when we talk about the glycolysis, is dihydroxyacetone phosphate. But we don't have a phosphate here. So what this one? Dihydroxyacetone. Is this a sugar? Yes, it's also a sugar, but what's the difference? D-glycerols. This is a aldehyde group. So we call this is aldose. Okay, dihydroxyacetone phosphates. We also had a carbonyl group, but the carbonyl group is ketone. So what we call this guy, this is ketones or ketones. So we have aldose and ketones. We had from C3 go to C4 or C3. We have C4 could be C4 could be C5. C5, C6, and C6. Go a long chain. Not very long. It's go like 8 or 9. What do we call these? You see these, the chemical components are exactly the same. Chemical structure is little difference. You either have aldehyde or you have a ketone. So what we call? This is the isomer. What's the isomer we call it? This is constitutional isomer. The sugar, the carbohydrates, even the monosaccharides have 4 different types of the isomers. We will mention about later on. This is just an example. One of the isomer is called constitutional isomer. Now, when we talk about D and L, what this means we talk about is enantiomer. Is that right? That's another isomer. Enantiomer we will talk about. So D versus L, this is enantiomer. We will talk about that later. Okay, so this is the introduction here about that. Now, let's talk about the very interesting family tree for the aldose. The ketones, we're not going to talk too much. Because except fructose, in the food chemistry, it doesn't talk too much about ketones. Basically, major they focus on is for aldose. And we already said 99% of our nature monosaccharides is deconfiguration. So we're going to talk about the dealdose from the beginning to the end. We want to give you some examples, okay? So when we start talking about it, we started from diglycerols. And we write it a little bit simple. So we have O, a dashed line, a horizontal line, and a small box. We start from here. Now how are we going to do? Each represents a different chemical. Here we had O, which means CHO, aldehyde group, and you have this horizontal line. This means hydroxy bonds or hydroxy group, and the last one you have this box, and we call CH2OH. That is always at the bottom. So let's start from the first one. This is 3 carbon. So how we call it? Since it's aldose, so we call it a triose. Okay, let's see this one right here. This is triose. Now, the question is, aldose, we have 3 carbon, we call it triose. How about the ketose? Now, here the number you always know, so as a letter. TRI means 3. OSE means sugar. But how are we different? Aldose and the ketose. You're going to do TRIULOSE. Add UL there. Triose. That means it's a 3 carbon ketose. Okay? Now, let's do like a family tree. This is very interesting. What I like to do every semester. We go here. And very simple, you don't need to worry about anything. You're going to draw this. We're going to draw like here. Exactly the same. We don't do anything at this moment. Now we're going to add up the hydroxy bonds there. I'm going to one on the right and the one on the left. So what this means, this becomes 4 carbon. We call it tetrose. Okay, so here this becomes tetrose. Same thing, what this means, tetralose. That's for ketose. Now what are the name of these two? This is called erythose. And this is called cereose. Okay, now we're gonna go here. This is gonna go here. And this is also gonna have gone to 2. So then the same thing. We're gonna draw here. 2 line, 2 line. Okay. Then go here. 2 line, 2 line. It's very simple. We go here. We go 1 line, go here. And we go here. We will draw 1 line, in the box. Okay, now we're going to add something there. Or we're going to add it. This always add on the right, then add on the left, then add on the right, add on the left. Okay, what are these? 5 carbon. What's the name of the 5 carbon sugar? We know. Pentose phosphate pathway. So it is pentose. So here we're going to write it is pentose. Same thing, if it's ketose, what do we say? Pentolose. Okay, now what are these two? This one you know. This is called a ribose. So you know ribose. DNA, deoxyribose, RNA, ribose. We know that. That's where they come from. Now what is this guy? arabinose. Arabinose. I want to make sure the spelling is correct. Arabinose. Arabinose, remember you have a lacto operon. We learned in the genetic class. We have arabinose operon also, which is a positive and negative control they combine. Okay, now what is this guy? Axolose. What's the last one? Lysose. L-Y-X-O-S-E, not S, L-Y-X-O-S-E. So I'll have to add X. Okay. That's L-Y-X-O-S-E. Okay, what is this guy? X-Y-L-O-S-E. I'm a microbiologist. What I learned is sugar is from the microbiology lab. Did you ever heard of XLT4 agar? This is agar's very selective media for salmonella. Salmonella grows there will become black colony. What does these three stands for? This is axolose. What is L? Lysine. Epsilon amino acid. What's T for? Tergitophore. It's a very selective antimicrobials. That's why it's a very selective media for salmonella. And if you have a heat injured cell, it now will be recovered. So you need to overlay with TSA to let injured cell recover, because TSA, tropic soil agar, is a non-selective media. Okay, this is something very interesting in the microbiology. We talk about that. Okay, now let's go to 6 carbon. 6 carbon, because it is important, so we're gonna go this way. Okay, let's draw the same thing. Don't worry about these too much. We got 3 line goes here. We first of all draw 3 line goes here. Go left, right, go here. Okay, now we're gonna add it. Where are we gonna add? We're gonna add on the right. We're gonna add on the left. Okay, what is this first one? Of course, this is 6 carbon. I'm gonna write here. 6 carbon hexose. Okay, so here, hexose. This is for aldose, for ketose, H-E-X-U-L-O-S-E. Hexulose. Okay, this guy, what is this guy? Allose. Allose. What is this guy? Altrose. This we barely heard about it. To be honest, I forgot about it. It doesn't matter. We don't mention these too much. Now we go here. This arabinose is a big deal. Okay, arabinose here. We're gonna draw this. So go 2 line right here. Then go here. So you go here. We're gonna draw. Sorry, this line I made a mistake. This line should be here. Okay, so this here is 2 line. Okay, now what we have to add. Okay, add 1 on the right, add 1 on the left. What is this guy? Everybody knows. Glucose. What is this guy? Mannose. Glucose, we will talk in much more detail, okay? Sorry. That spelling is G-glucose. Okay, now axolose. Axolose also could be separated. So I go here. Didn't draw very well. So what we do, we're going to draw this guy also. Go here. So what we have is 1 line, 1 line, 1 line. And we're going to go here. Same thing. This is very interesting. If you like it, you will find it's very fun. Go here and go here. What is this one? This one we don't mention too much. This is called glucose. That's why I made a spelling mistake, because my mind is already thinking about this one, glucose. Now what is this guy? This guy is iodose. This we don't talk too much. Okay, now the last section, which is nitrous, become 2. So how they become 2? So last section, and the same thing we're going to draw. What we have is left, right. When we go here, left, right, we draw it like here. What is this guy? Now we haven't added yet, okay? Right and left. This guy you know. Good. Lactose. This is the key we're going to mention. How about last one? Tyrose. This one we don't talk too much. Okay, so this is a process like a family tree from 3 carbon triose, 4 carbon sugar, tetrose, 5 carbon pentose, to 6 carbon hexose. And we already mentioned if it's ketose, you're going to add UL before OSE. It's very simple to remember about that. Now we want to mention something. It's very interesting we draw here. Glucose and mannose. It is an isomer. Majority of them all look same. The only difference is carbon number 2. Glucose go right, mannose go left, which what I mean is hydroxy group, which is OH, go right and left. So what is this one? These two, we call it carbon 2 epimer. Okay, how about the glucose and the galactose? If you look very detailed about the glucose and the galactose, they all look very similar. What's the difference? 1, 2, 3, 4. 1, 2, 3, 4 is this guy. The others are the same. So glucose and galactose, we always talk about them together, especially we talk about lacto-operin during the genetic class or microbiology class. Why they are always same? Oh, because it's carbon number 4 epimer. So this gives us a third isomerization happens during the sugar, which is called epimer. We will do a conclusion later on when we talk about that. Okay, so here we finish the talk about is second section. Give you an overview using the aldose to see the family tree of them, how they developed. Now, of course, it could be long and long, but we don't worry about those too much because in the food processing until hexose, later on is only the trace amount. And usually 5 carbon, 6 carbon, we will mention more during the food processing. Okay, now next one. Let's talk about a very interesting one, which is glucose. Okay, so we need to focus talk about glucose. So let's talk about glucose. What is the structure of the glucose? And everybody should know how to write it. COH at the beginning, then you have a very long chain. Not really long, but it's long. CH2OH. I usually draw these things on the top. Okay, there you go. HOH. H, this has to be picky. If it's in a chemistry class, then the O has to be connected with C. Okay, then you have H, CH, you have H, CH. And we draw this a couple of times in the blackboard during this semester. What is this called? This is called Fisher projection or Fisher configuration. Now, where this comes from? This comes from a long time ago when people doing the chemistry structure analysis at the very beginning, even early 90s, early 20th century, later 19th century, they want to see is in a linear structure what it looks like. Because every sugar, same as our glycerols, we could talk about, there is a carbon C right here. Okay, so you have this is the tyrosine, and you also have this guy. It's a tyrosine. What do we have? We mentioned we have a wedge, and we have a slash. Now, if we put our eye, go this direction, 45 degree, the chemist tells you it looks like that. So that is what a Fisher projection originally comes from. Okay, now what are we missing here? We are missing here is, we do not know the space shape, which is a spatial shape. Because we always want to see the 3D images, or even 4D, 5D, that's later on to come out. By the time they want to see the 3D images, so they come out with another configuration, which is we know Haworth's projection. But there is some story behind this Haworth's projection. Okay, it's very interesting. So we want to dig a hole, talk about more detail about this guy. So what it looks like, the Haworth's projection. Let's say the Haworth's projection originally, it looks like this. See, this is aldehyde group. And how do they find it? They did this in a slight acid solution. Of course, they're using a crystal sugar. Just put only one crystal there. We call it ice sugar. Put it there, melt it. Then what they find? They find it's very interesting. This is actually 90 degree perpendicular. So what it looks like? CHO, I already wrote it. Think about this 90 degree. You have LH, OH, you have OH, H, go down, have OH, H. Okay, the tricky thing is right on the top here. This you're gonna have is, originally you have AOH, you have H at the bottom. So you have H at the bottom. I'll use a different color. H at the bottom and OH on the top. And then the CH2 right here. Okay, first of all they find it like this guy. Okay, now they think about different. Okay, what are the different ones? They could go two directions. So what's the first direction they could go? They assume this could become just naturally reacted here. So I just draw it simple. Okay, that's a sugar like this. They become CH2. They have an O, and they go here is CH. They become like that. What is that one? If you count 1, 2, 3, 4, 5, 6, 7. What is that? This is 7 carbon chemical ring. They have a theoretical theory, talk about that. They could form 7 carbon chemical ring. However, our nature never existed these type of chemicals. Why? because from the physics standpoint, it is thermodynamic unstable. So our nature reject that. I can give you a joke, you will remember that. This is like you go to the casino. You play the dice. If 2 dice add up with 7, then the host will take all your money. Once the 7 happens, everything is gone. This is the same thing. The nature will attract everything. So non-existing. Then what happened? This we're going to go back to here. What happened is this do a rotation. Okay, this the carbon number 5, they do the rotation. When they do the rotation, what happens? This CH2OH is go down. So what happened? We can draw it. That's why I like to draw here. Then we can explain to you what happened here. It's a very interesting story. The CHO, and you have H, OH, OH, H, OH, H. So you go here. Once it's turned a degree, 90 degree, even more than that. It's some 120 degree maybe. This goes down. This H goes down. And this goes up. And what happened is, this OH goes here. Which means this rotation present oxygen atom to the aldehyde group. Now there's something going to happen. This is what we talked about before. Okay, let's go review. What is the electron arrangement of the sublayer orbital of O? That's why we want to talk about this, okay? 1s2, up, down, 2s2, up, down. Then here, what happened? 2p4. So you have up, 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 down. Okay. How about the carbon? What's a carbon looks like? Let's just draw this. 1s2, 2s2, 2p2. So what looks like? Up, down, following Hans rule and the Pauli exclusion policy. We mention all the time. This is up, this is up. What you find? Right here and right here. This could be connected because a long pair of electron, and we already mentioned in the food products is much more complicated than this model because this is a triplet. It could become a singlet. Okay, so they're going to react with each other. What happened? We say this is a long pair with this long pair. They're going to be connected with each other. Now what's going to be this guy go? This guy going to go here. This H is going to go here. That is what happened. We have so far a very common structure for a glucose is this guy. Is what happened for the Hayward's projection is CH2OH and this guy is O. Okay, that's what comes out. Now, what this tells you? This tells you you could see is a spatial view. So Hayward's projection, you could see a spatial view. And what else we could tell us? You had a carbon chiral center 1, 2, 3, 4 originally. And here you had a new carbon 1 chiral center. What this means, after this reaction, you will have a new carbon center. Remember, this is one section, this is another section, this is a section, another section is right here. That's why it's a new carbon center. And we also call it anomeric carbon. So what this tells you? This tells you the sugar, the crystal glucose dissolved in acid, slight acid solution. It could change from Fischer configuration, Fischer projection to Hayward's projection. And what's the chiral carbon number for the Hayward's projection? It becomes 1, 2, 3, 4, 5. How many are here? 3, 4, 5. There are 4 chiral carbon here. Here, there is 5 chiral carbon. So what this tells you? From Fischer to Hayward's configuration, add 1 chiral carbon. That's what the function finally becomes. And from the energy standpoint, it's more stable compared to the 7 chemical ring. Okay, now, this brings you another thing will happen. Since we have this structure, okay, we have this structure. Let's draw one more time. It's a very beautiful structure. The history, they're spending a lot of time talking about this. So we have OH, H. Okay, we have H, OH. We have OH, H. So we go down. We have OH, H, H, CH2OH. Okay, this new carbon comes out something. That could be on the top, and that also could be at the bottom. Okay, then this comes out another question. This is we call beta, this is we call alpha. What that one called? This gives you a new topic, which is this carbon number 1 added there. It becomes beta D-glucopyranose. This is alpha D-glucopyranose. Okay, now you have these type of theory about that. Using this configuration, you're not going to see it very clearly. Ian, can you move it? Can you move it to the other side? So, what we have, it becomes a third configuration comes out, which is called chair configuration. Okay, chair configuration is always difficult to draw. I try my best. Go here, somehow like that. Okay, not draw very well. Okay, chair configuration, what tells you? You can see the angle of bond view. You can see the angle. Okay, now let's redraw it. I need to look at my notebook. This one I didn't draw very well all the time. Let's just redraw it because we're going to explain this to you. So let's draw it. We're going to be doing like here, here. Oh, and here. That's angle is got up. Go here and go here. Okay, let's just draw like this. Okay, what's happened? Sometimes you draw this is tricky. This gives you something. Every time UH is writing like this, okay? Up, this is down, this is up, and this is down, regardless of where the others. Because H is axial level, we just say axial level. Axial position, we all call it. Okay, where are going to be the OH go? The OH they go is little bit angle here, and this is a little bit angle here, little bit angle here, little bit angle here, and this goes CH2OH. Okay, what is OH position? Equatorial. And the equatorial, we already said, if the OH is slightly above the axial position, we call it beta. If this guy is go down, and the H is go up, we call this is alpha equatorial position. Okay, this is a very interesting stuff. We're going to talk about is a new phenomenon, very interesting in the glucose. The terminology called mutarotation. What this means? This means if I have a crystal glucose dissolved in warm water, we'll just say warm water, it is not a single isomer comes out. It will be rich equilibrium status of isomers. What are those isomers? What are the equilibrium status of the isomers? It is alpha D glucopyranose coexisting with beta D glucopyranose. These are the two isomers. We give them another name since we call it anomeric. C, it is anomer. So this is a false isomerization of a glucose. It could be the anomer isomerization. So this is a formula. In 1910s, there is a scientist named by Henderson come out a very interesting equation for the K value. The K equilibrium equals 0.0096 add 0.025. The concentration of proton add 9.75. The concentration of hydroxy. Okay? I added the 1 0 there, so add 0.5. What this tells you? Tells you the transition between D-glucopyranose and alpha-glucopyranose. It really depends on the solution, whether you have the huge amount of the hydroxy, which means whether it's alkaline or not, because the effect of this hydroxy is 40,000 more than the proton concentration. When you see the formula, you understand about that. This is one conclusion they got it. The second conclusion what they got it is the temperature. Every 10 to 15 degrees Celsius, the temperature increase. The motorization, the reaction speed will up 1.5 to 3 times. Which means in a warm water, it is more happens a different combination of the animal, either alpha or beta. Now, then the research has been done to see a crystal glucose dissolved in the warm water. What are these components? What's the percentage? And it's very interesting. Our nature favor beta D glucopyranols compared to alpha D glucopyranols, and the ratio is approximately 64% versus 36%. Okay, this is one we talk about the glucose. How about galactose? It's very interesting results. If you dissolve a galactose crystal into the warm water, it will come out 4 different isomers, anomers, which will be alpha D galactopyranols, beta D galactopyranols. Since we already talked about it could be happen is a ketose comes out. So they are coexisting. Alpha D for alpha D galactopyranols.